So I'm currently at NTT and used to be in Paris. Before that, I don't usually do a lot of teaching, so I thought maybe I'll start the lecture with a story from my PhD advisor, Luca Trevisan. So when I was a PhD student, at some point I was talking to a friend who was a TA, a teaching assistant in MIT, and he was teaching very well. He got a teaching award. So I asked him what his secret to teaching well was, because I was struggling to teach. And he said the secret to teaching well is to dress well so that the boys, or rather the guys, will want to, no, sorry, so that the girls will like you and the guys will want to be like you. So I'm like, okay, all right, that's interesting. So I went with this story back to my PhD advisor, Luca Trevisan. He thought for a while and he said, well, that's a complexity theorist approach to solving a hard problem. We reduce it to an even harder problem. So I still haven't figured out how to teach well or to dress well, but hopefully in this lecture I'll be able to convince you that building lattice-based crypto systems is actually not hard at all. So I'll be talking about encrypted computation from lattices. This is the first of 3 lectures, and then will be followed by Shweta Agrawal giving the other 2. A bit of background and motivation. So we now live in the era of big data and AI, where we generate and collect and store a lot of sensitive data. And one thing we'd like to do is come up with ways to be able to compute on this data, and at the same time for utility, so that we can do also crazy stuff with it, but at the same time protecting the privacy of this data. All right, so this talk is about cryptographic mechanisms that allows us to simultaneously achieve privacy and utility. And broadly, these cryptographic mechanisms we refer to as encrypted computation. And in this talk, I'll be presenting 3 different notions of encrypted computation and how they can be instantiated from lattices. And the nice thing about this construction is that they are all about just sort of understanding one very simple equation. So I'm going to try to derive this equation and then go on to the constructions. Okay. All right, so probably the most well-known of these notions of encrypted computation is that of fully homomorphic encryption. So let me tell you what fully homomorphic encryption is. But before that, let me start with plain encryption, which is basically the same as the notion of private key encryption that Daniele talked about earlier. So in private key encryption, we have 2 algorithms, the encryption algorithm and decryption algorithm. That's just a key generation, but we're going to ignore that for now. And that both of the encryption and decryption algorithm gets a secret key. Right? The basic correctness requirement is that if you encrypt a message X using the secret key to get a ciphertext, and then after that you can decrypt the ciphertext using the secret key, you should get back the message that you started out with. All right, that's the basic correctness or functionality requirement. We also have a security requirement, which says that if you see an encryption of X and you don't know what the secret key is, you should learn nothing whatsoever about X. Okay? So that's basically the basic notion of encryption. And fully homomorphic encryption is a stronger notion of encryption, which satisfies both the basic security and functionality requirement. In addition, it satisfies additional functionality requirement, which is what we call a homomorphic evaluation. What this means is that if you are given an encryption of X without knowing the secret key, that the evaluation algorithm that given any function f can compute an encryption of f of x. And we refer to this algorithm that computes the encryption of f of x as homomorphic evaluation. Okay? What's very important here is that the encryption algorithm does not need to know the secret key. I'm sorry, the homomorphic evaluation algorithm does not need to know the secret key. Okay, so fully homomorphic encryption, or FHE for short, is very useful. It can be used for a lot of privacy preserving type applications. For instance, you have a user with sensitive data like health data or financial data. This user can encrypt this data using a FHE scheme and send it to a service provider in the cloud. And this service provider in the cloud can then maybe run some machine learning algorithms on this data, all right? And then get this encrypted output, send it back to the user, and the user will be able to decrypt it and learn the output. Okay, so this allows the user to have a service provider do some computation on this data while not having to protecting full privacy of the data, right? Not having to leak anything about the data to this service provider. All right, so there's something very useful, and prior to so this notion of FHE is not new. It's been around since like the late 70s. But for a very long time, the only FHE schemes we had were for us only supported very simple homomorphic computations like addition and linear functions. That's the one that Daniele also talked about. And the big breakthrough happened maybe about 15 years ago now, where Gentry and then followed by Rappe-Niemirska and Vaikuntanathan showed how you can construct FHE that supports homomorphic evaluation of basically any computation you want, they refer to as circuits, from lattice assumptions. So the original construction by Gentry used slightly more ad hoc lattice assumptions. The follow-up of Rappe-Niemirska and Vaikuntanathan does it from the standard LW assumption. That's the LW assumption that Daniele talked about earlier, and here we're going to be using the same assumption, except our notation is going to be a bit different. Okay? Instead of calling A S plus E, we're going to call it SB plus E. So instead of A, we have B, and instead of AS, we have SB. So it's basically the version that Daniele described, but transpose. Okay? So one good trick to have in mind for doing lattice-based crypto is that I find it very useful to just draw a picture. Right? Do you have a row vector or a column vector? Do you have a white matrix or a tall matrix? Just draw the picture on the board, and then that's that. Okay? And then I don't keep track of transposes or anything like that anymore. Okay? So in this talk, most of my vectors are going to be row vectors, but basically the picture is the one over here. All right? So my LW matrix is called B instead of A. Okay, so this is the LW assumption. And the scheme that we'll be seeing today, I'm going to show you an FHE scheme. And the construction that I'll be describing today is actually one due to Gentry, Sahar, and Waters. So the nice thing about this scheme is that it's extremely simple and give rise to this one equation that I talked about that enables also other encrypted computation type applications. All right? So this is actually not going to be the most efficient scheme that people use in practice these days, but it's the simplest. All right? All right, so I'm going to tell you what the FHE scheme looks like, and we're going to derive this scheme sort of from first principles. Okay? So our goal again is to construct FHE scheme which satisfy your basic notion of security and functionality. Usually, when you see a talk and you see a talk that presents FHE, you will start with a scheme that's secure but not fully homomorphic, and then try to make it fully homomorphic. Okay? In this talk, we're going to take a slightly different approach. We're going to start by trying to build a fully homomorphic encryption scheme that is not secure. All right? And then we'll try to make it secure after that. Okay? Now, if you want a fully homomorphic encryption scheme that's not secure, that's really easy. The encryption of X is just X, and then the homomorphic evaluation algorithm just takes F and computes it on X. All right? So that doesn't quite work. The insecure scheme we have has a nice property that it has more edit distance from a secure scheme. Okay? So the one where this identity map has a large edit distance from the secure scheme. All right? All right, so let me tell you what the insecure scheme looks like. So first, let me tell you how to encrypt. Before I tell you how to encrypt, let me first tell you what the secret key looks like. Okay? So again, our goal is to build a scheme that's fully homomorphic. We don't care about security for now. Okay, we just want functionality. We're not going to be able to hide the message, but we're going to give that up for now. Okay? So the secret key is going to be a row vector, all right, over ZQ. So think of it as a uniformly random vector over ZQ. All right, that's my secret key. My encryption of X is going to be a square matrix. Okay, it's going to be a uniformly random square matrix, so uniformly random mod Q, subject to the following constraint: that T times X is X times T. Okay. In other words, my encryption of X is a square matrix whose eigenvector is T and eigenvalue is X. Okay, so from linear algebra concept, if you haven't heard eigenvector and eigenvalues before, it's just this equation. Okay. Now, how do you sample such an A? It's actually not hard. You can basically, if you know T, you can basically do Gaussian elimination or something and solve for a random A, such that T times A equals to X times T. Okay, that will be my encryption. Okay. It's going to be insecure. It's not hard to see that's insecure. Basically, you can break the security of the scheme using Gaussian elimination, but that's sort of okay for now. All right. Now, the question is, how do you perform homomorphic computation? All right. In particular, so in general, if you want to do homomorphic computation for circuits, it's sufficient just to be able to do handle addition and multiplication. Right. Oh, let me say for now that my message space is going to be, think of it as a bit. Okay, I'm trying to encrypt bits, so xi is the number, it is 0 or 1. Okay, the schema for now actually allows you to encrypt ZQ values, but let's just think of the input as bits for now. Okay, or ZQ, either is fine. Right? So now what I want to do for fully homomorphic evaluation is to be able to, given encryption of x1 and x2, produce an encryption of x1 plus x2, and also to be able to produce an encryption of x1 times x2 without ever knowing the secret key. Okay? Now let me first show you how to do addition. So in particular, addition is fairly simple. So if you have two ciphertexts that are encryption of x1 and x2, so A1 is encryption of x1 and A2 is encryption of A2. If you add A1 and A2, it's actually going to be an encryption of x1 and plus x2. Okay? Just because if you multiply A1 plus A2 by T on the left, you get x1 plus x2 times T. So it satisfies our syntax for correctness. Okay. Any questions for addition? All right, so good. So now we want to be able to do multiplication. Okay? So I give you matrices A1 and A2 such that T times A1 is x1T, T times A2 is x2T. I want to produce a new matrix such that T times blah is x1 times x2 times T. Okay, any suggestions for what blah should be? It's not a trick question. But, I'm sorry? That's correct. A1, A2, exactly. All right? So T times A1, A2 is going to be equal to x1 times x2 times T. All right? So if you've seen eigenvectors and eigenvalues before, this is not surprising, but this is something you can derive from first principles. Right? So T times A1 times A2, if you multiply T by A1 first, you get x1 times T. Right? Then now this T multiplies by A2. T times A2 is x2 times T. So you get T times A1 times x2 equals to x1, x2, T. Okay, and this works just generalizes to basically any polynomial. For instance, if I want to homomorphically evaluate x1 times x2 plus x3 times x4, I just compute a1 times a2 plus a3 times a4. Okay. More generally, if I want to evaluate any polynomial, I can basically, the homomorphic evaluation algorithm basically treats the, basically evaluates the polynomial on with this matrices as the input. Okay, you can define a notion of evaluating a polynomial on matrices. Just do the natural one and it actually works. Okay? So now you have a scheme that supports homomorphic computation for polynomials. And it's not hard to see also that this gives you a homomorphic evaluation algorithm for general circuits, which can think of as just having addition and multiplication gates. All right, so that's it. So we satisfy our basic requirement, which is that we have a scheme that's fully homomorphic. Any questions so far? Okay, all right, but we really also want a scheme that's secure. All right, so now we're going to proceed in steps. So now I'm going to show you how to modify the scheme to get security. But along the way, we're going to lose the homomorphic evaluation property. Then we're going to try to fix that, and then we're going to be going around in circles, but eventually everything will work out. Okay, so let's now focus on trying to fix the security issue. So recall, it's actually not hard to see, basically the attack, remember the semantic security, you actually want to use the same secret key to encrypt many bits. Okay? So if you're given T times AI equals to AI xit exactly equal, and you're given many ciphertexts, you're basically getting many equations in the unknowns T, so you can do Gaussian elimination to solve for T. Okay? So basically, if you want to defeat the Gaussian elimination attack, then basically the idea is basically to do what the LW assumption is about. The intuition basically is that if you add noise, then Gaussian elimination is hard. Okay, so basically we want to avoid Gaussian elimination. So what we'll do is that we're going to modify our scheme as follows. So now, instead, when we encrypt xi, instead of picking ai such that t times ai is equal to xi times t, we're going to pick a random ai so that t times ai is close to xi times t. What does close to mean? In the same sense as LWE. So t times ai is going to be xi times t plus some error term. Okay? Put aside the issue of how do we sample such an AI. We'll address the issue later. But this is basically what our encryption will look like. You need to do a bit of work, but you can basically show that from the LW assumption, this scheme is going to be secure. We'll do it a bit more carefully later, but basically if you do it this way, you're not going to have a security issue anymore. Okay, so this is our new ciphertext. Let's see what happens when we try to perform homomorphic addition and homomorphic multiplication. All right. Also, again, we're given A1 and A2. We want to produce an encryption of x1 plus x2. Turns out the same thing as before works. If you want to homomorphically add ciphertext, you just add the two matrices together. Okay? And you can see that T times A1 plus A2 is close to x1 plus x2 times t. This is basically the same reason as what Daniel talked about when he said this additively homomorphic encryption scheme. The basic idea is basically, t times a1 is close to x1 times t, t plus a2 is close to x2 times t. If you add everything together, you get this equation. And using the fact that small plus small is still small. Your new small is slightly bigger than your original small, but we're friends here. Let's just pretend for now all smalls are the same small. Okay, so that's sort of fine. That takes care of addition. Now, what happens with multiplication? Okay. Now, if we try to do the same thing that we did before, actually it doesn't quite work anymore. If you multiply t by a1 times a2, it's not going to be close to x1 times x2 times t. If you try to do the previous reasoning from before, basically the reasoning from before crucially uses the fact that things are 0 and not small. The problem comes up here is that basically if you do t times a1 times a2, you can replace t times a1 by x1 times t plus small, but then this small gets multiplied by the a2, and a2 is big, so when you multiply small by something big, you get something big. So it's not going to be close to x1 times x2 times t. However, if you can somehow guarantee that the xi's are small, then you're going to be fine. Okay? So, good. So then this gives us the following template for building a fully homomorphic encryption scheme. Okay? So if A2 is small, then small times A2 is small, then everything should be fine. Right? So this will generalize, like before, to handling any polynomials. Okay? So you can just add and multiply the matrices together. All right. So with this in mind, we now have the following template for building a fully homomorphic encryption scheme. All you need is to have a scheme that satisfies the following three properties. Okay? An encryption of X is a matrix A such that T times A is close to X times T. Okay? For security, you're going to require that A hides X. And in addition, for the homomorphic property, you also want to require that the entries of A are small. Okay? And if you have all these three properties, then you're done. Addition is just adding two matrices together, and multiplication is just multiplying two matrices together. Okay? So now, how do we design a scheme with all of these properties? Okay? And achieve security under the LW assumption. Okay? So now we just need to focus on this template, and we don't have to think about addition and multiplication anymore. All right, so let's try to do all these three things. We're going to do it incrementally. We'll try to satisfy the first requirement first, which is the T times A is close to X times T. Okay, so what does our scheme look like? T is not going to be quite uniformly random. It's going to look like S followed by -1. So S is basically plays the role of the LW sequence. Okay, so this is my T. So what does my A look like? Well, first observe that if I multiply S minus 1 by B stacked on top of SB plus E, you get the error term E, which is small. Okay, so that's good. But what you want is to have X times T on the right-hand side, whereas now you have 0 on the right-hand side. Okay? This basically says if I have a matrix that's eigenvalue 0, how do I turn it into a matrix with eigenvector x? Okay, what you do basically is just to add x times I to b atop SB plus E. Okay, then t times the first term is close to 0, and t times x times I is x times t. Okay, so that gives us the scheme that satisfies the first requirement. So an encryption of A looks a bit like this expression over here. SB plus E plus X times I, right? And it's going to satisfy the equation on the top left. Okay? Moreover, it's actually quite easy to see from the LW assumption that this A hides X. Okay? By the LW assumption, B and SB plus E is pseudo-random, so you can replace B and SB plus E by a uniformly random matrix. And then this uniformly matrix can serve as a one-time pad to information theoretically hide X plus I. So this follows from the LW assumption that this ciphertext A hides X. All right. Now, however, the main problem now is that this A is not small. Okay, so B is going to be uniformly random. SB plus E looks random, so this thing is in general going to be a matrix with very large entries. Okay, close to Q over 2, that's it. All right, so how do we make it small? All right, so what we're going to do is, right, so we're going to take a generic approach to turn a matrix into a matrix of small entries. Okay, how do we do? So for instance, if you want to, you have a number in ZQ and you want to turn it into a vector with small entries, you just do the basically the bit decomposition or the binary decomposition. All right, that's basically what we're going to do. Okay, here's a general approach. Suppose I have a matrix M over ZQ. I want to turn it into a matrix that's small. In fact, I want to turn it into a matrix of 0, 1 entries. All right. How do I turn a matrix into a matrix of 0, 1 entries? Basically, I'm going to take the matrix and blow up the height by a factor of log Q. Okay, so I'm going to create a new matrix with log Q blocks. Each block is going to have the same dimension as my original matrix M. Okay. The top block is going to contain the least significant bits of every entry in M. Okay. And the bottom block is going to be contain the most significant bit of every entry in M. Okay. And then the blocks in the middle will be the second least significant bit, the third least significant bit, and so on and so forth. So this is sort of the natural thing to do. So basically, we're considering the binary representation of every entry in M. Okay. Except we arrange it in a very specific way. The top block is the least significant bits, and then the bottom block is most significant bits, and then interpolate the whole thing. Okay. Why do we pick this particular representation? It has the following very nice property. By the way, first note that going from M to this representation is actually a nonlinear operation. But what's nice is that the inverse of it is actually a linear operation. Okay. In particular, if you look at what's called the gadget matrix, this is basically the gadget matrix that Daniele talked about, maybe slightly permuted. Okay, so what's the gadget matrix here? It's going to the matrix that's very wide. The first block on the left is the identity, followed by 2 times the identity, 4 times the identity, up to Q over 2 times the identity. Okay. Assume for simplicity that Q is the power of 2. Now, if you multiply the gadget matrix by this matrix that corresponds to the binary representation of M, you're actually going to get the M back. Okay. You basically get I times the least significant bits, 2I times the second least significant bits. So you assemble everything together, you get exactly M back. Okay. And for this reason, we're going to, because G times this thing is the thing M on the left, we're going to denote this binary representation by G inverse of M. Okay. So this G inverse of M is just a notation. G inverse is not the matrix inverse of G. Because G is wide, matrix inverse isn't necessarily well defined. Okay. We're just calling it G inverse because it has this nice property that it looks like G and G inverse cancel, and then you get M. It's more like the functional inverse of G. All right, so this is our G inverse notation. So given any matrix M, G inverse of M outputs a matrix of 0, 1 entries that corresponds to the least significant bits up to the most significant bits. And the property here is that M is going to be equal to G times G inverse times M. So I have a question over there.
Right, so the question, repeat the question.
Yeah. All right. So the question is, where does the least significant bit to the most significant bit comes from? So I'm referring to the least significant bits. These bits are related to the entries of M. Right? So this is sort of the binary representation of every entry in M. So the least significant bits will be the least significant bit of every entry in M. Then the most significant bit is the most significant bit of every entry in M. And then you go in between from the least significant bit to the most significant bit. Does that make sense? Are there any other questions? Okay. Good. So this is the property that we have. Right? So this gives you a generic way to take any matrix that potentially has large entries, that's from 0 to a Q minus 1, and turn it into a matrix that has 0, 1 entries. All right, and that's what we're going to do. We have our candidate A, except the candidate A has large entries, and we want our A to have small entries. So what do? We apply this G inverse operator. So we apply our G inverse operator to the A with large entries. We get back a matrix with small entries. It's going to be much taller than the matrix that we had earlier. All right, and if you the problem now is that if you introduce the G inverse and you want the same right hand side, then you have to introduce a G to cancel out the G inverse. Okay, so now we have the following equation. All right, which comes very close to what we want. we have our A, which is, which has small entries. And G inverse doesn't change the fact that A has X. So this new A will still have X. The main problem now is that instead of T times A is close to X times T, we have T times G times A is close to X times T. So instead of, so we don't quite get the, we get the second and third property, but we lose the first property because instead of T, we have T times G. Okay? So to fix this, we're going to rename T times G to T. Okay? So we're going to define our new T to be the old T times G. Okay? So that sort of fixes the problem. So now on the left-hand side, we have the new T times A. Right? The problem is now on the right-hand side with X times the old T. We want it to be X times the new T. So there's a missing G, so that's not hard to fix. So basically, if you change the X times I to X times G, you will get X times T times G on the right-hand side. And now if you call T times G or new T, then you get all of the properties. Okay, so then T times A, the new T times A is going to be X times the new T, so that's the first property. A is going to hide X. Okay, because the big A hides X, the G inverse version will still hide X. And the entries of A is now small. Okay, and that's our fully homomorphic encryption scheme from LWE. Any questions?
There is something that doesn't compile for me. There's something that doesn't compile for me, because if we remove the G on the rightmost place, then we already had this, this identity. And then multiplying by G would likely break this identity. And
okay, so that's the question is how do you get correctness? That's your question, right?
Yes, this
okay,
seems to break correctness.
Right, yeah, good. So actually it doesn't. So if you, if you want to check that this equation holds, the G and the G inverse cancel out, so you can ignore the G and the G inverse. Okay? Then you know the new T multiplied by the first term, which is B and SB plus E, is going to be small. And then you get the new T multiplied by X multiplied by G. So you get X times the new T. So basically, this G over here gives you that G over.
Ah, okay. So the point that I missed was that we added G inside of the parentheses. Thank you.
Yes, sorry. Yeah, right, exactly. So to make sure that the G appears on the right-hand side, you add the G on the inside. Yeah. So in fact, there's a bit of cheating here. So when you replace identity by G, which is wider, your B will also need to become wider, just so that your addition makes sense. Okay, any questions? Okay, so that's the whole scheme. All right. So so that sort of works, except there's this G and G inverse floating around, which we don't really want to deal with. So the modern interpretation of this scheme is to sort of ignore the G and G inverse. So what we're going to do is, instead of thinking about the new T, we're going to think about the old T. Right? So we're going to remove the G and the G inverse. So that's your equation over here. Right? And instead, so we're going to keep the old T, except the right-hand side is not T, but T times G. But we'll just call this our new equation. Okay, what does that mean? So it's more convenient to ignore the requirement that A is small, but rather just require our correctness, our basic correctness requirement, instead of T times A is close to X times T. Our basic correctness requirement is that T times A is close to X times T times G. Okay, that's a more convenient way to think about the whole construction. Then addition is still the same as before. If you add, if you have A that satisfies the property that T times A is close to X times T times G, then if you have A1 and A2 satisfying the equations for X1 and X2, if you add them together, you have T times A1 plus A2 is close to X1 plus X2 times T times G. So that's good. For multiplication, then you do something different. Instead of multiplying A1 by A2, you multiply A1 by G inverse of A2. Okay, then you can see that T times A1 is going to be X1 times T times G. Then the G will cancel out the G inverse, and then you get X2 times T times X2 times X1 times X2 times T times G, and then you get X2 times X1 times X2 times T times G on the right-hand side. Okay, so this is sort of the modern way of looking at things. And if you write it this way, you start realizing that, wow, if I want to multiply X1 by X2 by X3, if you do the natural thing and you multiply X1 by X2 first and then multiply by X3, then you get something like A1 times G inverse of A2 times G inverse of A3. Okay? And actually, that's a different way to multiply A1 by A2 by X1 by X2 by X3, which is to multiply X2 by X3 first, then multiply by X1. Okay. If you do it this way, your homomorphic evaluation becomes X1 times G inverse of A2 times G inverse of X3. So the difference is sort of where the brackets are aligned. And turns out this is the better way of doing things, because if you keep track of the noise terms, this will actually have a smaller noise. So by sort of multiplying your, so the order in which you do your multiplication actually really matters. So that's a clever way to do it, and then there's a not so clever way of doing it that incurs large noise. Okay, so that's the right way to do it. If you do everything the right way, you have the property that you can evaluate polynomials where your error grows with the degree of the polynomial multiplied by polynomial of lambda, where lambda is security parameter. And more generally for general circuits, you can also do the same thing, except your error grows exponentially in the depth of the circuit. So that's sort of your basic FHE scheme. One shortcoming is for this GSW scheme is that your ciphertext are rectangular matrices, so they're pretty wide. So in practice, for those of you who are familiar with TFHE and VU and more recent schemes, they actually do a slightly different scheme so that your ciphertext are smaller. Okay. But the algebra is slightly more delicate. So we're not going to go there. We're going to stick to this scheme. Okay, so that's all I'm going to say about FHE, I think. Okay, any questions about FHE? Yeah.
So for the evaluation of the multiplication, there we have the A2 matrix. Does it also include a new error term, or don't we need that one because there's already one in A1?
Yeah, so... Okay, so the question is in the A2 matrix, the error term. Yeah, there's going to be error term in the A1 and the A2 and the A3. Yeah, they all have error terms. So your new error is a bit hard to describe. It's sort of for multiplication. So for addition, your new error is the sum of the two old errors. For multiplication, it's actually going to be the old error for A1 times G inverse of A2 plus sort of the error for the new A2 term.
Okay, thanks.
Yeah, you have to evaluate it a bit carefully. In fact, it's going to get multiplied by either x1 or x2, so you actually need the fact that both x1 and x2 are bits. Questions? Okay, good. So right, so that's all I'm going to say about FHE. Right. So like I said at the beginning, all these new constructions all boils down to one equation. So this is the first. This is sort of the first step to the new equation. So now I'm going to try to show you how to derive this new equation. Okay. So to motivate the new equation, I'm going to go back to our insecure scheme. Okay. In our insecure scheme, the functionality, the fully homomorphic property of our insecure scheme basically boils down to the following lemma. If you have a bunch of matrices AI, such that T times AI is Xi times T, right, then you can, from the AI, derive a matrix AF, which corresponds essentially to evaluating the polynomial f on these AI matrices. This AF is going to have the property that T times AF is equal to f of x times T. Okay? Yeah, so this works for, right. So that's basically what the correctness boils down to. It's just a matter of manipulating eigenvectors. Okay? In particular, you can move all the terms on the right-hand side to the left-hand side. So here's a restatement, equivalent restatement of the same equation, which is that if T times AI minus Xi times I is 0, then T times AF minus f of Xi is 0 for any polynomial f. Okay? And now we want to generalize this lemma to something stronger. Why do we want to generalize it? A bit hard to motivate, but it's going to be useful. What kind of generalization do we want? We want a generalization that applies to any matrices AIs. Okay? So the lemma 1 only applies to matrices that have eigenvectors T. So I want a generalization that does not talk about T's, does not talk about eigenvectors, and works for any matrix AIs. Okay, so I want a formula that sort of relates AI minus Xi times I, okay, and AF minus f of x times I. That is a generalization of lemma 1. Okay, I'm going to tell you what the generalization. I'm going to tell you what the new statement is, and then I'm going to explain to you why it implies lemma 1, and then I'm going to show you the proof. So the generalization is going to look like this. It's going to say that for all AIs, and for all x, and for all function f, there exists a matrix H, okay, such that if you look at the AI minus x times I, when multiplied by this matrix H, it's going to give you the expression on the right. Okay, that's a generalization. Before telling you why such a statement may be true, let me convince you that lemma 2 is a strengthening of lemma 1. Okay, so I want to show that lemma 2 implies lemma 1, and the proof is very simple. Basically, multiply, why does lemma 2 imply lemma 1? Multiply both sides of 2 by t. Okay, so on the left-hand side, the precondition for lemma 1 will tell us that on the left-hand side, you're going to get 0 times the H matrix. Okay? And 0 times the H matrix is going to be 0, so that means that the right-hand side is 0, and rather that means that t times the right-hand side of lemma 2 is going to be 0, which is exactly the right-hand side of lemma 1. Okay? So indeed, lemma 2 is a generalization of lemma 1. And we know lemma 1, well, we know 2 implies 1, we know that 1 is true, it doesn't imply that 2 is true. Okay, so we still need to prove 2. Okay, so let's try to prove 2. And like in our RPG scheme, to prove 2, it's sufficient to just prove 2 for addition and for multiplication. Okay, so let's see what the proof for lemma 2 looks like for addition. Okay, so this is basically what I want to show. All right. So I want to construct a matrix H so that, you know, this thing times H is equal to A1 plus A2 minus X1 plus X2 times I. Okay, so the vertical bar, oops, I should have said this, sorry. The vertical bar corresponds to a concatenation. Okay, so concatenation, so your bunch of matrices is just concatenation, you know, in the horizontal sense. Okay, so any guesses as to what the H matrix looks like? This one might be slightly tricky. Any brave?
I concatenated with I.
Oh, I'm sorry, the same thing.
I concatenated with I.
Yeah.
Good. Yeah. So you just put identity. Yeah? So if you multiply, you know, if you multiply this, then this, you get this plus this, which is exactly the right side. Any questions? Okay, good. So what about multiplication? Okay, so this is roughly what we want. Okay, so for multiplication, the right-hand side, the A sub f is going to be A1 times A2. All right, so we want something that has a property that gives you this equation. It's not going to be so. This is going to be slightly trickier. The first thing you notice is that, well, we kind of want to put A2 on top, so that A1 times A2 gives you A1 times A2. Okay, then you need to put something at the bottom. Turns out X1I works, so that X2I times X1I gives you X1 X2I, and then there's a cross term, which is X1 times A2. It's going to get cancelled out by the A2 times X1. Okay, so this is exactly the H matrix that we want. Okay, so that's sort of your proof for addition and multiplication. You want to do it for more general function, you just sort of compose all of this computation together. Okay, any question? Okay, all right, that concludes the proof for lemma 2. But what we really need for application, oh, sorry. Oh, yeah, there's a question. Okay, good.
So just very quickly, what happens with A's to square the terms that we have?
What are the comments for the A's?
Okay, never mind. I misparsed it. Never mind. Sorry.
So basically, in this case, the A's are square matrices, and you want this thing to hold for all square matrices, and your H is allowed to depend on the A's, just given the order of quantifiers. And also allowed to depend on F, and also allowed to depend on the X. Okay. All right, so for our application, we're going to need a stronger version of this statement, where instead of square matrices, we are going to replace AIs by a much wider matrix, and we're going to replace our I with the gadget matrix. Okay. So, right, so in particular, we want the case, we basically want the same equation, except the I is replaced by the gadget matrix, the A's are much wider, and with the addition requirement that the H matrix has low norm. So the entries of the H matrix are required to be small. Okay, and this is going to be the one key equation that basically gives you everything in advanced lattice-based crypto. All right? So this is equation we want, and this is what we call a lemma 2 star. Okay? And let me convince you that lemma 2 star implies lemma 1 star, where lemma 1 star is basically what we use for our FHE scheme. Not the version, not the insecure version, but the secure version, but not the one with the I, but the alternative version. Okay? So, which says that if T times AI is close to Xi times G, times T times G, then T times AF is close to F of X times T times G. Okay? Why does lemma 2 implies lemma 1? The proof is similar to the version with exactly equal from earlier. You multiply the both sides of lemma 2 by T on the left-hand side. And now you observe that the precondition in lemma 1 is going to tell you that T multiplied by the stuff on the left is going to be small. And since H is small, small times small is going to be small. So that means that T times the right-hand side is small, and that means that T times A of F is close to F of X times TG. Okay? So T times the right-hand side is small, so that gives you the right-hand side on the lemma 1. All right. So in particular, this equation, once you prove lemma 2, you get an alternative derivation of a fully homomorphic encryption scheme, okay? Where AF is basically your homomorphic evaluation algorithm. Okay. So now let's try to prove this stronger version, the souped up lemma 2. Okay. I'm going to prove this statement is sufficient to just handle addition and multiplication. So, all right, so for addition, this is the equation that we want to prove. And basically, you can use the same H for the addition as before. The nice thing is the OH is just identity followed by identity, and this is a low norm matrix. So you get it for free. For multiplication, it's a bit trickier. If you try to use the same matrix from before, you get this A2 on top of Xi times the identity matrix. Now, if you assume that the Xi are bits, then the bottom part is going to be small. Okay? But the top part, A2, is going to be big. Right? So then what you do to make the, when you have something big and you want to make it small, you basically put in G inverse of A2 over there. Right? Then you basically get the equation you want. Now A sub F for multiplication is going to be A1 times G inverse of A2. Again, the cross terms are going to cancel out. X1 times G G inverse of A2 is going to be X1 times A2, which will cancel out by cancel A2 times X1. So you get exactly what you want. Okay, so that sort of proves the statement for addition and multiplication, and you can just compose the whole thing and you get it for any circuit as well. Any questions? Okay, so this basically is the equation that gives you basically all of advanced lattice-based crypto from lattices. The most important property I want to highlight about this equation is the property of the A sub F matrix. Okay. What I want to emphasize here is that the AI and the AF matrix, the AI and the AF matrix have the same dimensions. Okay, they're going to be wide matrices. The height is going to be n, which is essentially the length of your RWE secret. The width is going to be n log q. And in particular, the dimensions of these matrices do not depend on the size of the circuit F, and do not depend on the number of X that you have. Okay, so that's not depend on L. And that's a very useful property because A sub F is basically a compressed version of the circuit F. So it does actually, once you work out the parameters, you're actually you need to set the n and log q to be polynomial security parameter and the depth of the circuit. The depth of the circuit kicks in because of the noise growth that you get from homomorphic evaluation, which also gives you this noise growth in this H matrix. Okay. The entries of the H matrix are going to grow exponentially in depth of the circuit. So for correctness, you will need n and log q to be polynomial depth of the circuit. Okay. So if you take this into consideration, then the description of the A sub F matrix, by which I mean the number of bits that you need to specify the A sub F matrix, is going to grow with the depth of the circuit, but does not depend on the size of the circuits or the length of the X, which is L. Okay, that's going to be a very useful property, and we'll see that come in these two other notions of encrypted computation that I promised. Okay. So this version I'll describe is not going to be quite encrypted computation. It's more like commitments rather than encryption. But let's pretend that it's some sort of encryption for now. So I'm going to give you a construction of so-called functional commitments. Okay. Before I tell you what functional commitments is, let me first tell you what a commitment scheme is. So commitment scheme basically is sort of like you want to commit to a message X. Okay? It's basically as if you take a message X, you put it in a box and you put a lock on it. Okay? And then after that, there's an opening phase, which is essentially like a key, so that if I combine the opening with the commitment, you get back the original message X. Okay? But given just the commitment itself, the X is fixed and you cannot change your X. Okay? So a bit more concretely, a commitment scheme has the following syntax. You have a commitment algorithm that takes as input a CRS, like a common reference string, and a message X, and produces a commitment, we call it sigma, and a state, which is used for computing the opening. All right? There'll be an open algorithm that, given the state, produces an opening, we call it pi. And then basically, there's a verification algorithm that, given the opening and the value that you claim you open to, outputs 0 or 1. Okay? The basic correctness requirement says that if you have a commitment to X, and you provide an opening to X, and your verification algorithm gets X as inputs, the verification algorithm should output as set. Okay, and the standard security requirements says binding and hiding. The basic binding says that basically the commitment, when you have a commitment sigma, it fixes the message that you're committing to. Okay? So you cannot produce a commitment sigma and be able to open it to 2 different values. Okay, once you have a commitment, you can only open the 1 value. The commitment uniquely determines values that you're committing to. Typically, in a commitment scheme, we have a hiding property, which says that the commitment should hide the message. But for this talk, we're going to focus on a slightly different notion, and that's succinctness, which only says that the size of the commitment is much smaller than the size of X. Okay. This in particular implies some notion of hiding because the commitment is short, so information theoretically loses information about the message. But it could still leak a tiny bit about information about the message. But we're going to be happy with succinctness for now. And that's important for applications where you basically want to commit to a long message with a very small commitment. So if it, for instance, your standard Merkle-Darmstadt hashing or your Merkle tree will satisfy these requirements of a commitment scheme. It's going to be binding and the commitment is short. So we're going to be interested in a strengthening of function of commitment that we call functional commitment. And here, instead of trying to commit to a string, you want to commit to a function. All right, think of a function as a big function. Think of a function as like a polynomial or a multilinear polynomial or a circuit. But think of it as basically a polynomial. The f is going to be much bigger than the input. Okay, so instead of committing to a string, you're going to commit to a function, and the opening is going to be specific to an x. So given an x, you can provide an opening, so that given the opening and the commitment, you can recover f of x. Okay? So unlike before, where you're committing to x and you're opening to x, here you're committing to a function f, and you want to open to f of x. Okay? And that's sort of the functional commitment primitive that we're interested in. So in particular now, our open algorithm takes as input additional input x, produces a proof, and the verifier given the x and the candidate value y that's trying to open to, try to check whether y is f of x. Okay. So basic correctness is going to say that if you commit to f and you provide a value opening to x, for x, you should be able to verify to f of x. You should open the value f of x, and security says that given a commitment and a value x, you should not be able to open to 2 different values of f of x. Okay, so in some sense, given the commitment and the x, there's only 1 possible opening. And succinctness now says that both the commitment and the opening should be much smaller than the size of the circuit F. Okay, so that's sort of the construction of functional commitments. And right, so so this is actually very new work. So only like last year that we have the first functional commitment for circuits. So we are able to where you can commit to any circuits and produce an opening to f of x. All right. So this is a very new result from a year ago, and the security of the scheme relies on lattices, in particular the sys assumption, which is weaker than LWE. All right. Let me just quickly tell you what the construction looks like. So that's going to be CRS in the sky. So in particular, if you are interested in committing to a function that takes L bit inputs, then the CRS is just the matrices A1 up to AL. Okay, these are your A matrices from the previous magical equation. And your component of F is going to be A sub F. So as I was saying before, the magic property of A sub F is that it's very small. In particular, the bit size of A sub F is polynomial security and the depth of the circuit. So that gives you a succinctness property. So you get a succinct complement to the function F, and that's really the one thing I want to highlight. The A sub F is a complement to F. All right. And the opening is going to be this H matrix, the low norm H matrix that I mentioned. Okay. And the verification equation basically just checks that the opening is small, and it satisfies this equation that we talked about earlier. All right, so A minus Xig times this H matrix if AF minus F of Xg. So correctness follows from the equation that we mentioned earlier, and security basically follows from the SIS assumption. It's not hard to show that if you can open the two different values, you recover a trapdoor for the matrix on the left, which particularly breaks SIS for the A matrices. That's basically all I'm going to say about this construction. Any other questions? Yeah.
So one thing that feels kind of worrisome is that when we recall the definition of HFX for addition, it didn't actually depend on the axis. And in the multiplication one of them depended on A and not on X. So why is this not a problem?
Good. So, so the question is that the A's don't depend on the X. So it is very important. So first of all, in functional commitment, you're committing to a function F. So when you're committing, you actually don't know what X is going to be. Okay? So it is very important that, so it is useful that the A sub F does not depend on the X. Otherwise, your commitment is not going to be well defined. Okay? But if you look at our construction from before, basically the matrix H is going to depend on X. Right? And that's going to be okay, because when you are producing the opening, you actually know what X is going to be. And you know what the A's are going to be, so you'll be able to produce the H matrix, which corresponds to your opening.
Yes, but if we go back to the plus case, then it doesn't actually depend on X. And that feels suspicious, because maybe then we could cook up some commitments without even knowing what X is.
Okay, so the question is depending on X. So first let me say that the verification algorithm does depend on X. Okay, so there's some sense that X is involved. Now I want to say that the definition of functional commitment, the security guarantee, says that given a commitment to F, and X, you cannot open F of X to two different values. Okay? But there is no guarantee that when you produce an opening to F of X, that there exists an F that's consistent with the F of X. So the security actually does not guarantee that there's an F that's consistent with the F of X. And that's sort of okay. You just want to guarantee that you cannot produce open to two different values.
What I meant was, suppose that F is the addition of X1 and X2. Then HFX is just the stacked identity matrix. And then it has nothing to do with the X's. And in which way then it can be an opening if it that doesn't even depend on X in any way whatsoever for that particular function?
Yeah, so let's say it's addition, then AF is A1 plus A2, right? So it is true that for addition, the opening does not depend on X itself.
And why is it not a problem?
For addition, it's not a problem. I don't have a good explanation of why it's not a problem, but I'll have to think a bit more to see where the problem might be.
Thank you.
Yeah. But for multiplication, it does depend on the X.
I just want to point out that even for multiplication, it only depends on half the x's, not on all of them. Right? It only, sorry. I was just pointing out that, like in addition, he was saying it does not depend on x at all. And even in multiplication, it does not depend on all the bits of x. It only depends on half of them. So in some sense, it's not like the multiplication is really encoding the whole x either. I just wanted to point that out.
Yeah, that's a good point. So somehow you can produce the opening without knowing, the opening does not depend on all of your x. Yeah, I agree. I never thought about why this seems strange, but seems okay.
So you mentioned that you only care about kind of binding. So what does it mean for applications? So where do we not care? So we only care that we cannot produce two different openings, but we do not care about these openings necessarily being consistent. So what does it, like some applications
so
where we don't care about, like, yeah, just thinking.
So for application, do you care about the size of the opening? Is that the question?
So if I understood correctly, you said for the security property, we only care about not being, so that no one can produce openings to two different things, like an open at two different values. But you said we don't care about someone is able to produce an opening to a value that's inconsistent with the function.
Right. So there's no guarantee that the.
question is like, what does it mean for applications like of this thing? Where can we not care about this?
Yeah, so good. So the question is, so the guarantee here is actually pretty weak. So if you are considering application like Stunks, you actually do require a stronger notion of security. Okay. Which says that there exists an F that's consistent with the opening values here. But this does not achieve that stronger requirement.
Okay.
Yeah. So, right. So I do want to say that there is a succiness requirement for the opening. The openings cannot be too big. In this construction, the size of the opening is going to depend on the length of L. Okay, but we do want the openings to be just smaller than the size of the circuit. So if you think of the circuit as much bigger than L, then the size of the opening is still sublinear in the size of the function. So you can hope to have a stronger succiness requirement, which says that the size of the opening does not depend on the length of X, and that is not achieved by this construction. Any other questions? Okay, good question. I'll try to think offline a bit more about why the fact that the opening that depends on X is not a problem. Good. So now I want to do one more application. All right, and that's actually going to be essentially the end of the first part of this thing. Okay. All right. So the other application we'll talk about is going to be a notion called laconic function evaluation. So this is sort of a generalization of an earlier notion of laconic oblivious transfer. So this is a notion that's actually very related to the FHE application that we described at the beginning of the talk. So you have a user, we call Alice, which holds some input X. You have Bob, the server, that has some function F. Okay? And so that we are interested in computing F on X while protecting the privacy of X. In our earlier FHE application, Alice holds X, and Alice wants to learn the F of X. Okay? In this new application, Bob is the one that wants to learn F of X. Okay? So think about Google wanting to run a machine learning model, a machine learning algorithm on your inputs, and Google wants to know what the model is. Okay? And we want to be able to do this in a way that only has a two-message protocol. Right? So we want to have a two-message protocol that achieves this functionality. So in particular, Bob will send one message. Alice will send a second message that depends on Bob's first message and depends on X. Okay? And from these two messages, Bob should learn F of X. And moreover, we have the requirement that the second message, which we call the ciphertext, should only learn F of X. So the correctness says that you need to leak F of X, and that's all. It should hide everything else about X. Okay? So, right. So here we also want a strong efficiency requirement, which is that, well, if Bob is the one that wants to learn F of X, then Bob should be the one doing all the work that's computing F of X. Okay? In particular, the efficiency of the protocol from Alice's point of view should be basically the same as sending F of X in the clear. Okay? So the computational requirement on Alice should be that it's much Alice runs faster than having to compute f of x. So if you think about your standard two-party computation protocol, it sort of satisfies the syntax, but they generally have the property that Alice needs to, the amount of work that Alice needs to do grows with the size of f. Okay, and here we want a protocol where Alice runs in very fast time. Okay? So Google wants to learn the machine learning model. Google should do all the work of doing all the computation. Okay? That's the current requirement. Is that a question? Okay, great. Okay, so FHE actually solves this problem. You can solve this problem using FHE, but you will need 3 messages. So Alice will send an encryption of x to Bob. Bob will homomorphically evaluate f to produce an encryption of f of x, and then Alice will decrypt and send f of x back. Okay, that will give you a protocol that satisfies the security and the efficiency requirement, but it will have 3 messages. Okay. Here we really want a 2-message protocol. Bob talks, Alice talks, that's it. Okay? All right. In particular, if we want the requirement that Alice's computation complexity is very small, it should also be the case that the first message from Bob, which we call the digest, has to be a short message. If the first message is going to be very long, just reading the message is going to take a very long time. Okay? So the first message should be much shorter than the size of the function f. Right? So what does construction look like? So if you want anything that's cryptographic and sort of has this property that is sort of it's about f and much more than f, it's just a sub f. Okay? So the first message is going to be you're going to pick this A1 to AL matrices, and it's going to contain a sub f. Okay, that's the first message. I'm actually not going to say what the second message is, but basically it's going to be related to the key equation, but with some additional LWE samples. Okay? That's basically, roughly speaking, what the construction looks like. Any questions? Okay, great. All right, so let me conclude. I'm going to finish a bit early, and then you can have a longer coffee break. So in the first part of this talk, we talked about how how you can use lattices to realize 3 different primitives related to encrypted computation. And at the core of all of this relation is the following very simple equation. So this gives you all of this reconstruction. So what's important here is this A sub f matrix is very small, and that gives you your functional commitment, the short commuted function f, and also gives you the short message from the server in laconic function evaluation. Okay, so in the next 2 parts of the lecture by Shweta about encrypted computation on lattices, she's going to tell you about lattice trapdoors and how to use lattice trapdoors together with this equation to realize an advanced form of encryption called attribute-based encryption. And that's it. Thank you.
Maybe first, are there any questions to Hoeteck? There's a question over there. Verna, there's a question.
Am I right that we can implement any functionality we want, be just restricted in which corresponding operator we using within f of x, I mean eigenvector? Sorry, may I just recall the question? The question is about restrictions in which functionality we can implement. Are we restricted by which operator we could write down under f of x, I mean linear operator?
Also, the question is sort of in all this construction, does it depend what operator you use for the to define the function f, or
which restrictions we have for f of x? Which functionality we could learn? And
which function do you care about for the f, for the applications?
Yep, and is it restricted to any linear operator we could use? Any linear operator could be, which could be decomposed by eigenvectors. Am I right?
Maybe you take this question offline.
Okay.
Okay, thanks. So let's, there's one more question over there.
Maybe I can answer.
There's an answer to the question.
So I have another question, but maybe I can actually answer the previous question. So if your question is, which functions can we compute like this, right? It turns out with this addition and multiplication, you can just compute any function.
Yes,
that's the question. So you can actually have any function. Of course, the size of the circuit kind of depends on it. So of course, it could be inefficient if you choose, I don't know, busy beaver function or something. But so my question was just when you said the three-step solution to the final thing with fully homomorphic encryption. So we would also have to prove that this decryption that we get at the end, right, is the correct decryption somehow. So we would have to add even some other primitive there to make sure that the verifier really sends the correct f of x value at the end.
Good. So the definition of the conic function evaluation, at least for the basic construction, we're only interested in semi-honest security. So we're only interested in a setting where where everybody follows the protocol execution. So there's no worry about you're computing the wrong f of x, at least for the basic construction. So if you want stronger security notion, you can probably, for instance, need a snark to make sure that, for instance, if you want to guarantee, for instance, that the first message is computed consistently with some f, then you need to do some snark to make sure that that is well formed. If the first message is not well formed, you could potentially leak additional information about xp or f of x.
Okay, thank you.
Yeah. So to go back to the previous question, right? So in addition, we talked about in this talk we talked about using addition and multiplication gates. So they play an analog to sort of in circuits 101. You can build any circuit using AND gates and OR gates and NOT gates. But in practice, you may want to if you have specific class of functions in mind, you may not necessarily want to represent the function using addition and multiplication gates. You may want to think about a different way to represent the function and try to optimize your homomorphic evaluation algorithms for that class of functions so that everything runs faster. So that's sort of a bit of so this is sort of just a proof of concept construction, right? In practice, you probably really do want to optimize this thing for specific functions. And then you want to also optimize the representation of those functions.